So as it was discussed in the previous session, like deep learning based algorithms for power systems, particularly in the microgrids, this time we're shifting our focus towards mm, the deep learning based energy management systems for electric vehicles. So why energy management systems but not electrical vehicles in complete? Because when you're looking at a electric drive kind of setup in your electric vehicles, so again it is a DC PMSM motor or induction motor which is being driven by a power converter. Okay, so that is again have control algorithm basically, which was same as your DRL algorithms which we were discussing, like DQN, DDPG, TD3. So that kind of an algorithm will be straight away used for your electric drives. So we have no much complications in that aspect. So we are looking from the more the energy management system perspective, because you have a lot of sensors, lot of information that is coming into play, and how that need to be handled. And one of the challenging aspect is your battery management. Okay, so in electric vehicles, one of the challenging is that energy battery management. And when I'm going through the recent literature, in December 2024 itself, MDPA has called for various deep learning applications for electric vehicles. So they have around 17 articles in that, and I will be discussing 5 or 6 top articles, like 5 6 top articles out of those 17. And along with that, we'll also discussing certain foundational things. Okay, so what to expect from this particular lecture is common hurdles in electric vehicles, why such hurdles need to be addressed, transforming such tasks into lingo of machine learning. Because whenever you have a task in your hand, being an electrical engineer, if you can translate that kind of a problem into a form of machine learning problem, then you can pull out existing machine learning algorithms. Okay, you have certain problem. Okay, say you have to predict the solar energy, how much solar energy is there, but how much solar energy can be generated tomorrow. But if you know that, okay, this is called as a regression task in machine learning, then you can get, okay, then when you get that keyword, so immediately into the nomenclature of the machine of this computer science or the machine learning, then you can immediately take up all the algorithms that are under regression. If not, so you don't know, you want to predict solar energy, or you want to predict something, you don't, if you don't know the lingo or the keyword that will be used in machine learning, it will be a tough time. So that's why always understand the lingo of machine learning, for which attributes to your task in electrical engineering. And we'll see some machine learning basics. Even why we are stressing on machine learning, because deep learning has evolved from machine learning. Most of the algorithms today are, as I said, deep learning models are driven by neural networks. But if you see, the neural network foundations are in machine learning. So we'll see some basics of machine learning, and discussion on neural networks, SVM and Bayesian tree to some extent. And we'll see some other tasks like range estimation, battery life expectancy, and advanced deep learning algorithms, and so on and so forth. Okay, as per the availability of the time. So coming to why electrical vehicles, everyone know it's an eco-friendly. It is electricity source can be hybrid, higher efficiency. That is a combustion engine versus induction motor, internal combustion versus induction motor, low maintenance, low running cost, and all these things. Being an electrical engineer, you are aware of these competencies of electric vehicle that can be replacing the internal combustion or the conventional vehicles. But okay, whenever you're having such kind of a transformations, always you will be facing certain challenges. When you look at what are those common challenges when you are transforming yourself, or you want to make electric vehicle most prominent solution, so one of the problem is electricity source can be hybrid, but management of multiple sources demand complex strategies. So what does this mean about? So in IC engine, you have a fuel, and you know that for 1 liter petrol, you know that yes, you are going to get say 10 kilometers range or 15 kilometers range. But when it comes to electrical vehicle, when you have a battery state of charge of say 70% or 80%, and there are multiple sources on your your dashboard, it might be in the name of n number of things. So such kind of a complex energy system is there. You cannot easily say, okay, like how you did with your conventional petrol thing, you cannot say, okay, I have 70% soc, so I can go up to 100 kilometers. You cannot say like that straightforwardly. And second is the higher efficiency. uh, as we Yes, batteries are efficiently stored. Yes, motors are efficiently run, but do they work go on along in line with line? Do they see eye to eye is the question. Because multiple sources, multiple loads, and electrical motor, based upon the need and demand, the power should be allocated accordingly. So at that point of time, you have to deal with complex management, so which can impact your efficiency. And you want a low maintenance, you want to achieve low maintenance. But the issue is, if you cannot able to predict the battery life cycle, because one of the costliest part in your electric vehicle is an battery, if many people agree or not. But the battery life cycle estimation is very tough to say. Okay, if you buy a battery, can you confidently say that up to 4 5 years I will not have any issue with this battery? It is not a possible. Of course, you will not have a problem with the motor, but there are higher chances to have a problem with the battery. But that is not the context with IC engines. Do you think that IC engine, like the petrol to this internal combustion thing or internal combustion thing, which is generating the torque and speed for you, do you say that, okay, 3 4 years I don't know what will happen, or the fuel tank I don't know what will happen? No, that kind of a thing will not be there. So longevity is another crucial factor in electric vehicles. So you have to bring down the maintenance. So for that maintenance, one of the crucial aspect is your batteries. So batteries, if you are able to estimate the life cycle, okay, how much longer my battery can survive, or how many of course battery life will be said in terms of charge and discharge cycles. So you can say, okay, yes, this much battery cycles it can sustain or survive. And it has to have low running cost. So you have to have an optimal settings of your uh, so it should not having longer charging discharging cycles kind of a thing. So this is where the AI and DL is coming to play, so that to handle, because when you have multiple sensor data, you can aggregate the sensor data and you can make a beautiful knowledge out of it, and you can have an optimal outcome out of it. And real-time decision making, which is very much similar to the one of the points in our previous session, that it has to make real-time decision making. And in the grid, real-time decision making is needed. But in case of EV vehicle, real-time decision making is a unavoidable scenario. Okay, so when you're pressing a brake, if you're going with a regenerative braking or something like that, so then the field should be excited. If the flux is not going to your field with a pneumatic braking and kind of a thing, again, that is a question in hand. And whenever you are applying any kind of an speed, like when you're taking overtaking or something, you are supposed to give a speed boost. So at that point of time, the source should allow you to draw that much amount of power, right? So these all complications, even though that looks very simple from the outlook. And complex pattern recognitions, because the driving style of different drivers will be different. So they will be drawing how the speed torque characteristics will be dynamically being changed based upon the driver. So that's kind of a complex patterns need to be taken into account whenever you're making certain predictions. For example, how much fuel is left or how much long you can go. So those kind of predictions are dynamically changed with the driver's pattern. And also, not only that, the road pattern. So if the road is not good, or the sometimes EV vehicle model also can have an impact on that. Type of battery can have impact on that. Type of motor can have impact on that. So all those complex patterns need to be taken into account, and that complexity can be handled by AI and deep learning beautifully. Now, looking at certain applications, one is the EV range estimation. So, because this is actually one of the biggest stress busters for the users, because if I have one SOC, sorry, 1 liter or 2 liters, I know how much I will go. But in common vehicles, but in EV, okay, if I have this much of SOC, or how much long I can go, so that is the EV range estimation. Okay, I have this much of SOC, so these many kilometers I can go. Next is battery life prediction. Okay, how much time or I have this battery before it going dead. Okay, smart charging and scheduling. So how much I should be charging, when I should be charging. Not only that, when you are having some charging stations, how much should it be charged, when it should be charged, who should be charged, at what rate of dq by dt it should be charged. So those all things will be taken into account. Energy management in EVs, because you don't have only the motor but also different loads in the EV vehicle. So all those things need to be taken into account. And autonomous driving and control. So this might not be straight away coming into the realms of electrical engineering from the context of some colleges. But if you go to some premier institutes, see, even autonomous driving is taken by the electrical engineers. Okay, so because why people usually don't take it as electrical engineer, because they treat the image processing that is involved in this process is not belongs to electrical engineering. But if you go to any premier institutes like IIT Delhi, IIT Kharagpur, or IIT Bombay, image processing also will be done in electrical engineering. And along with that, because why this is crucial, because when you're doing an autonomous driving, you have to have something like lidar sensors, dist proximity sensors, and all these things, based upon which you will be making a decision of autonomous driving. So you have to have a multi-sensor data integration, so which can be prominently done by an electrical engineer or an electronics engineer. So that's why autonomous cybersecurity, because you have to have an always EV vehicles will be having a communication with the outside world. It might be in terms of GPS, or it might be in the terms of radio, or it might be in the terms of route prediction, all these things, or sometimes it might be a software update. But if that person who is that vehicle is attacked, cyber attacked, so that implies that that person is inside a car which is locked and got cyber attacked. So it is like a set of a jail for him, right? So even cyber attacks in cars are more dangerous. So even that aspect is also being explored. So when we have these basic tasks, like in previous and also we have this management, control, and design. So usually when it comes to EV, majority of the time it will be like estimation, identification, and control. Okay, so estimation, you will be using mostly regression, identification, sorry, estimation. Coming to identification, there is a mistake here. It is not continuous values, it is a discrete values. So it is supposed to be a classification, and control, it is a strategies of sequence of actions that will be taken. Okay. So let us look at some examples of estimation. Let's say continuous value, which how long can I travel with the remaining battery? How many cycles of batteries? How many cycles of batteries is left? What is the true signal from the sensor noisy data? Because sensor is sending a data which might be corrupted with noise, not with an attack, but with a noise. So I have to estimate what will be the correct value. Okay, correct value will not be discrete value like 0 or 1, like it can be like 2.96 or something like that. So how to accumulate the multi-sensor data, because you are getting data from multiple sensors, how to aggregate them to make one common data. So these all are coming under estimations, which is a continuous value. Coming to the next, to the identification value, which is the discrete. Okay, when it comes to discrete, is my car performing as per the standards or not? Okay, so this is like yes or no, which is putting in one of the discrete state. Next is there any anomaly in the car? Because sometimes the sensor is giving, it is the sensor might not be giving. It might be noisy data, it might be anomaly data. So when it is anomaly, it should be able to identify it. So this is kind of a discrete values. And continuous strategies, control strategies are very much prominent while you're having energy management, optimal solutions. Like you have to turn on something you because something has to be turned off or something like that. Sequence of actions that has to be taken up. So, okay, what should be the charging range and rates? When I mean rates, that is dq by dt. Charging range is like, okay, what should be the current range I should be using? How to optimize the utilization of energy, like I am having multiple loads, to which load the energy need to be distributed to optimally, and what actions need to be taken by the controller to match the characteristics or the load characteristics. So as I said, when you have an load with a particular torque speed characteristics, your motor has to match to that torque speed characteristic. So you will be changing the power converter outputs. But power converter output will be changed with the help of the gate signals. So the gate signals or the control signals will be given by your RL, or reinforcement learning. So first, looking at the EV range estimation, this is one of the papers which we have implemented, not part of that MDPA thing. We did something on our own. So we had a bunch of EV vehicles, and what we thought was, okay, why don't we predict the uh, time, okay, how many kilometers this EV can go with the current state of battery. Okay, so we used multi-layer perceptron, support vector machines, and random forest, and it was identified that the random forest is giving a good value, and the data set used is the sprintmotor.de. Okay, this is an open source data set with which anyone can try out. Of course, there are more prominent data sets that are available. So, but this is the experiments which we did in our lab. And next is the second case study, which we did is the battery life cycle prediction. So we want to, based upon the existing dq by dt's of the first 10 charge and discharge cycles, how many things can be left, how many charge and discharge cycles are remaining uh, until the battery goes dead. Good results, and we are able to predict like the remaining utility life with the first 20 cycles only, with varied kind of batteries. But it was identified that using transformers, which we have discussed previously, so transformers has a better implication, and it can predict with only less than 10 number of cycles, or first 10 cycles. Okay, and publicly data sets are available at matter.io and lithium ion batteries, and there are various data sets, because currently it is one of the most thriving uh, problem statement, that is what is the state of charge, RUL, battery life estimations. So these are one of the most thriving aspect of electrical engineering in EV vehicles. Okay, and you have lot of open data sets available. And once other thing is smart charging and scheduling. We have taken one example of one charging station, and we have randomly inflowing of this is all in simulation only. This is not in physical world, but the previous data sets are from the real world. So we have considered the data sets from the real world for the EV range estimation, and also the battery life cycle prediction. But coming to the smart charging and scheduling, we have considered a simulation model. And with the flow of this electric vehicles, so what should the charging and discharging that should, sorry, charging that should be done. And another is the energy management in EVs. So here we have used again deep reinforcement learning, particularly PPO and A3C, to have an energy management in EV vehicles. And we had one data set that is available from GitHub. We have taken that energy management data set in EV vehicles also. Autonomous vehicles is one more thing. Driving in EVs is something which we plan to take, but towards drones. But initial phases, it is understood that the convolution neural networks supported with reinforcement learning has a very good performance. Now, moving forward, when we are looking at, okay, that give you a big gist of, okay, deep learning has a lot of role to play in EV vehicles. But if you look at why this is all working out for machine learning or AI from a non-AI background, because it was conveyed that many of you are not from ML background. So when you want to have a basic understanding of ML, so ML is nothing but a program that will be designed. But what is the difference between a traditional programming and ML? Usually what happens is, in our conventional practices, you are given a data that is input like X, and you are supposed to predict some output like Y. But this is achieved by writing a program. This program will be written by a domain expert. So domain expert articulates certain rules in the name of mathematics, and that mathematics will be pushed into the program, into the computer. Okay. So given some X, it will be predicting Y. But what happens is, if this X becomes more complicated or the data becomes so huge, so the domain expert cannot write a mathematical model which can accommodate the complexities of the data or the task. So for that reason, people have relied on machine learning. So where given the data and the what is the anticipated output, the computer will give you the program. Okay. So once this program is given to you, then you can go back to your conventional practice. Okay, for the new data that is flowing, you already got the program, so you can estimate what could be the output for the newly given data. So this way, machine learning has taken down the load on the domain expert for assessing or going through thousands of examples for articulating rules or mathematical models for so that the program can be dumped into a computer for the predictions. Okay. Bring it into the lingo of machine learning. So why it is working out? Because machine learning is about improving performance at some task with experience. Because it is improving the performance on a certain task with experience is nothing but the data. When they look at data and they improve performance, so the performance is usually measured in terms of mean absolute error or mean square error, categorical entropy, binary cross entropy, categorical cross entropy. So this performance is measured with some sort of things. So and that measurement or the metric has to give a lower value for on a given task with the given data. So then you can say that that is a machine learning model. And whenever you have any kind of a task, so whenever you have any task in hand, so you will be looking at experience, metric. These are the two things which you are looking at. So experience is nothing but the data, and the metric is nothing but the measure on which you want to perform better. Okay. Performance metric. So if you say playing checkers or is like the task, so how can you say that machine learning is learning or a particular algorithm is learning? Because its performance is increasing on the data, on the experience. So how the performance is evaluated based upon number of games it won. So what is the data? A data is nothing but a database of multiple games played by different people. So given games played by different people in the name of experience, the learning algorithm has to learn certain program or rules such a way that the performance metric keeps on improving or keeps on better. If it's like a error, if the performance metric is error, then it has to go down. If the performance metric is like not penalty but like a reward, if it is a reward kind of a thing, it has to increase performance metric. If it is like something like penalty like error or something like that, the metric should go down. And in case of driving on 4-lane highways using vision sensors, if that is the task, so the data experience of the data is nothing but sequence of images and steering, like the okay, if this is the images what I'm getting, what should be my steering angle? So that will be the data, and how many average distance before the human judged error. So okay, when this kind of a data is given, so how much closer I'm getting to the performance of a human is one thing. And if you see the left bottom one, recognizing handwritten words, so the data will be like, okay, each handwritten word image will be there, and corresponding what is that word will be there. So this will be going as a data, and performance is like the, okay, prediction of code. I had this machine has created a word as like a, and apple, but what was the actual human word? So this comparison will be the performance metric, so on and so forth. You can have, whenever you have a task in hand, you have to create a data set in the name of experience, and that data set will have both input and output. So given this input, your model should be predicting the output, and the output, predicted output, should be closer to your uh, output in the data set. So whenever, when you have to use ML, so you will not be using ML as per your wish. So whenever there is a huge amount of human expertise is there, you will not use ML. But whenever human expertise does not exist, at that point of time, ML is used, because then you have to churn out new knowledge. So that is where the data science has come into play. So when you have huge amount of data, rather giving it to the humans and explicitly asking to draft the rules or craft the rules, you will ask the model to design or unveil the underlying relationships and the laws and principles. And the second one is when humans can't explain their expertise, like feature presentations. Usually this happens in medical field, sports, and these places where humans can make beautiful decisions, but the rules behind that decisions will be claimed as intuition or experience of the humans. And the third, models must be customized. So that means you have a human experience, but that knowledge has to be updated. That should be aggregated. That should be transformed to a different task. So in that point of the model, machine learning models will be used. So when learning is not useful, obviously when there is lot of human expertise available, and there is no need to learn uh, of the aspect in the given task, there is nothing to learn. So for example, if you are already given age, you need not to calculate age based upon your date of birth. Already date of birth information is available, so it is not point, there is no point of estimating the age. Already you can take a simple logical flow. So when you're looking at type of learning, you have supervised learning, you have unsupervised learning, you have semi-supervised learning, you have reinforcement learning. So supervised learning is you are given both X and Y, that is input and output are given in your data set, and you will learn from that. That is supervised learning. Unsupervised learning is you have only X, you don't have Y, that is the output. Then you are, if you are learning, then it is termed as unsupervised learning. Semi-supervised learning is in data set, you have multiple examples. For some examples, we have both input and output pairs, but some instances or some examples only input is present, output is not present. So when you want to learn the model based upon this uh, data, where some samples are having input and output, but some samples are not having any output, so that kind of a learning is termed as semi-supervised learning. So this is how a typical data set looks like, where input is like the features and output is like the label. So in this example, if you see all the examples, all the entries in the rows have a corresponding label. So this can be used. Supervised learning can be an approach that can be taken into. If say label is not at all given for any example, but only features are given for all the examples, then you can take up unsupervised learning. If say for say first 10 examples you have both features and labels, but for the rest of the examples you don't have labels but you have features, then it is termed as semi supervised learning. Now there is no question of not having features, because when the features are not given, there is no point of learning anything. So in supervised learning, you have again regression and classification. Regression is like, given an input, you want to predict a continuous output, so that is regression. When you have given an input, you want to have a discrete output, then it is called as a classification. So this is a decision boundary, how it is made. So in case of battery SOC, and you want to have miles left, that is how many miles you can go, that will be a continuous value, so that will be a regression. So when you are taking about battery discharging and the battery SOC, you can say that okay, whether the battery is going bad or battery is going good or battery is okay. So that was the classification task. And along with that, you have transfer learning and online learning. Transfer learning is very much useful in cases where you have lot of data set for similar task on a different domain, or sorry, similar domain but a different case. For example, you want to predict the battery remaining utility life based upon some parameters, input parameters. But what happened is, you are working for company B and you have the data set for company A. But company B battery is slightly different, and company B car is slightly different. But you have huge amount of data for company A's car and battery. So what you will do is, you train a model completely on company A's data, and you take only a small amount of data from company B, because only small amount of data is available with company B. Then you do something as a fine tuning or transfer learning. This way, the knowledge of the input parameters to battery life estimation of company A is slightly tweaked, because the underlying rules stay the same. Maybe the characteristics will change slightly here and there, but the underlying gross view of a relationship will stay the same. So if you are still confused, you can take the example of a shuttle bat player and a badminton player. So if you want to train it, if you are a badminton player and you want a partner. Now when you want a partner, you have two options: one picking from a shuttle player, one playing from a football player. But majority of the time you'll be picking up a shuttle player, because the rules of shuttle and badminton are very much closer. So the guy can easily transfer learn his shuttle playing skills into a badminton playing skills. But if you pick a football player, there is no correlation in the rules or the characteristics between football and the badminton. So that person, it is not at all possible for transfer any of his knowledge. It is like learning, it is making a new person to learn. So when you have a similar knowledge on the task on a different data set, you can bring it there. This kind of information, this kind of a transfer learning has equipped the deep learning realm to major extent, as to grow to a major extent. And online learning and active learning, these are very prominent things which will be used by industry, because say whenever you give a feedback of 4 rating, sorry, no, when you say spam or user kind of a thing, user inputs or something like that, so that will be like active learning. Online learning is like, whenever you have a model trained on a particular data set, okay, you train that model and you deployed that model, fine. Now after some time, this company will be getting new data. Now you want to update the model parameters based upon the flow of new data. So that updation of the model parameters with the help of the new data is termed as online learning. Now in this all these contexts, for a given x, you have a y, explicit y. Okay, given this, you are supposed to predict this. Okay, so this is very much evident, unless for the unsupervised learning. In majority of the scenario, it is equal. But there will be certain scenarios where uh, you will not get an output in the first moment itself. You will get an output after sequence of actions. For example, if you have a game to play, when you're playing a game, the game win or lose, you'll get to know after sequence of steps that have been taken. You'll not know from the first step or the second step itself you are winning a game or losing a game, but after sequence of steps only, or certain sequence of steps only, you get to know, okay, the game was won or lost. But until then you will not have this label, okay, winning or losing, but you have to take a sequence of steps. You have to predict the sequence of steps, so that is termed as reinforcement learning. So reinforcement learning, the model is termed as agent, and it will be interacting with an environment. You don't have the data set, you don't have the data set, you have the environment, so that the model can interact with the environment and get something called a state and reward. So basically, whenever agent interacts with the environment in the name of action, whenever an agent interacts with an environment, because the agent will give an action and the action will be interacting with the environment, so the environment will be changing its state. So when an environment is changing its state, the something reward will be given to the agent along with the state. Okay, so for suppose you want to do a synchronization, okay, in your electric power grid, something like that. Now maybe at point one, or maybe at first step of firing your switch or SCR, you will not be getting an result what is expected, but you will be closer to the result what is expected. So that will be like a reward. Yes, you are moving in the right direction, kind of an appreciation that is given by the environment. So with these new states and rewards, again agent will give another action. Now that action again will be fed to the environment, and the environment will now change to a new state and gives a new reward, and so on and so forth. It keeps on repeating until the environment reaches a state like winning or losing what is expected as an output. So this is reinforcement learning, which is very, very, very much useful in the context of control and management. You can also attribute it to your conventional control systems, where agent is like the controller, environment is like your plant. So agent is giving a control signal, and environment will give you the error. Okay, that is the plant will give you an error, right? So the error is again taken by your controller, and which again gives you your control signal. So when control signal is given to your plant, the plant will again give back you some sort of an error signal. So from error signal, the agent again creates some sort of a control signal. So this is an interplay between the plant and the controller until the plant reaches an output or creates an output which is a reference signal. So this is an analogy between the reinforcement learning and the conventional control. Very much analogous, because this is what I'm saying. When you have this lingo that is relating your conventional electrical engineering with the machine learning or the lingo, then you can pull out, okay, my control algorithms, actual my control strategies or my control problem is actually referred as reinforcement learning in machine learning. Then you can immediately go and search, okay, what are the various reinforcement learning algorithms in for these things. Then you immediately get a list of, okay, these are the reinforcement learning, these are very popular reinforcement learning algorithms, these are the old or classical reinforcement learning algorithms. So this way you should be able to understand the lingo of how an conventional machine learning lingo, or like electrical engineering lingo, can be problem lingo, can be translated into a machine learning lingo. And whatever we have spoken till this point about a reinforcement learning is being reflected as a graph representation here. So first, agent will take the states, the agent will take the states of the environment, and as per that it creates an action, and action will be taken by the environment and gives you new state and reward. Taking this new state and reward, agent will create an action again, and they will take in the action, and environment will create reward, new reward and state, so on and so forth. Okay, this is an iterative process. This is very often used in computer science for game theory, like training an virtual agent to play video games and so on and so forth. Training an agent to design dynamic pricing, that is in your electric vehicles, how much price it should be put so that people will be attracted to stop at your charging station, or how much price you have to put. Because if you look at energy markets, some people will sell in short energy markets basically. So within 1 week or these scenarios, okay, how many megawatts can be given, there will be a bidding process. Okay, for coming 1 week I will give this much of megawatts per day, for okay, I'm going to charge this much. So this is all um, bidding process can be optimized with the help of dynamic pricing, where again DRL will come into play. So basically, when you look at a machine learning pipeline, you will give in some raw data, which is nothing but your input. You will extract certain features with the help of domain expert, because domain expert will say, okay, for this output or for this task, these are the features that are important, and you create the feature extraction with that. And post that you will be uh, like uh, pre-processing the features, or standardization of the features will be done, so that all the features are in same range. Next, you will be identifying what are the important features of these. Like, all the information that is given as input need not be taken into consideration, so you can have an important features that can be identified, and then you will give to the ML algorithm. Okay, so in the raw data, you will extract the features that are uh, aligned with the task. And because, right, whenever you want to have a certain fault to be identified, you will look at these line currents at this particular thing, or you will compare these line currents with these voltages. So based upon the task, the kind of aspect you are looking at will be different. When the aspect is being different, the features will be different. So that particular features will be considered. And whenever you're considering those features should be standardized. Because say you're taking line currents, and yeah, and also voltages, the line currents will be having a different range. Like, it can be like a few tens of amperes, and your line voltage will be to few hundreds of few hundreds, in terms of few hundreds. So one is in tens range, one is in hundreds range. That kind of a disparity might influence your machine learning model. So what you do, you pre-process the complete data set, so that each feature or all the features in a standard range, that is 0 to 1, okay, or -1 to 1. And after this, when the features are given, maybe not all features that are felt important by the domain expert are needed. So based upon some feature subset selection, or the feature selection rules, like minimum redundancy, maximum relevance, these kind of branch and bound. So these kind of approaches, you can reduce the features. You can find the important features, and next you will train the ML model. So after training you use these features as input to train your ML model. So this is how a conventional ML ops. So these days they're calling this as ML ops. You have DevOps, and now you have ML ops. So ML ops is actually a subset of DevOps. This can be used. Okay, and looking at various algorithms that are used in machine learning, you have, one second, neural networks. You have neural networks. Okay. In previous scenario, we said, right, you have given X, you have a Y. Initially, you will start with some random values of M and B, and you keep on updating it through error back propagation. So if you take a random value of M and B, so here the chart is given. So this is M, this is B, and you have randomly chosen this value because you want to initialize with something. But optimal values of M and B is somewhere here. So how can you move from here to here? So it's very simple. You compute the error at this point of time, and you take a gradient of that error, and you move one step using the error back propagation. And again, you will have this as in your M and B values. So with this new M and B values, you will be again computing the gradient, and you will update your M and B, so on and so forth. You keep on moving at every step until you reach your target. Once you reach your target, usually your error will be zero. So if your error is zero, your gradient will be zero. So there will be no longer an update. So this is the iterative approach that was taken by error back propagation, where gradient computation is very much crucial. Like gradient of the error is one of the crucial aspect. Now, when you're doing this, there are various way of updating the weights. So based upon the error, so stochastic gradient descent, ADAM, adaptive gradient, RMS prop. Okay, so there are various approaches if for updating your weights. So you have a weight, you have predicted the error, and from the error, sorry, not predicted error, you have computed the error. So from the computed error, you are again computing the gradient, and you'll be using this gradient to update your weights. So how much should I okay, I got a gradient, fine, but how much should it be updated, or to what extent should be updated? So these all things will be taken care by these optimizers. So ADAM, Medagrad, RMS prop, SGD. So if you are very much an expert, and you know, when looking at the errors itself, you can say how much it should be updated and so on and so forth, you can take SGD. But if you are a novice like me who doesn't have any idea about how it should be updated, you take ADAM. Okay, but if you are using of course, ADAM is an updated version of Medagrad. But if you're using LSTMs, usually it is ADAM also works for LSTMs. In general, ADAM will work for all the neural networks. Okay. So these are the things which we have already seen, and we also had one demo. But if you can go to the stanford.edu/karpati/connet.js demo classify 2d.html, if you go to this particular link, you have very good demonstration of these neural networks. Okay, so it will be like a visual interpretation of the neural networks. So we'll look at this towards the end of the presentation if time permits, but you can take a screenshot of this, and accordingly you can go to this particular place where it gives a demo, like a visual interpretation of how neural networks will work out. And you not to install anything, everything works on your as it is written in JS, so it everything runs on your browser. So in neural networks, of course, many prominent things are like many prominent algorithms use ANN, artificial neural networks, where y hat is equal to a activation function of w1 x1 plus w2 a2 plus something, so on and so forth. CNN people are using, and RNN when you are moving away from towards the temporal features, you will be picking up recurrent neural networks. So recurrent neural networks and CNN, if you want to, as from an electrical engineer perspective, if you want to see, CNN is like an FIR filter, finite impulse response filter, and RNN is more like your IAR filter. So when it comes to FIR filter, your output is dependent upon current inputs and your previous inputs. Okay, that is what CNN or ANN is supposed to do. But when it comes to RNN, it's like IIR, where your current output is dependent on current input, previous inputs, and previous outputs also. That is what IIR does, infinite impulse response filter. But in RNN, rather than depending on the previous outputs, it is depend upon your previous hidden states. So that is the only change. But from a logic point of view, it's like CNN is like FIR, RNN is like a IIR, infinite impulse response. So RNN has some limitations. So they want to add on some memory cells so that you will not face something called a vanishing gradient. So LSTMs were taken into picture. So there are other variants also into the ANN family, but these four variants are most prominent. And in recent times, the temporal nature of RNN is merged with CNN, and they started to call this temporal convolutional networks, TCNs, temporal convolution networks. So that is a hybridization of CNN for temporal features. And support vector machines were designed in 1980s at that point of time, because we don't have lots of data at that point of time, but we need to have a generalized models or generalizable models. So in this context, they developed something called support vector machines. So support vector machines, rather considering the complete data sets to define a decision, they consider something called as support vectors, because whenever you want to make a decision, the decision will be made based upon the samples which are closer to the boundary. You might have millions on millions of samples farther away from the boundary. Even out of like 900 odd samples are away from the boundary, but only 100 samples are closer to the boundary. The boundary will be influenced by the 100 samples which are closer to the boundary. Okay, because you don't look at the pattern, or you will not consider the pattern from the farther samples. You will be considering the pattern from the closer samples of the boundary. So this is what support vector has identified and said that, okay, I will be designing a decision boundary based upon the closer samples, but how can I name those closer samples which are influencing me? So then it started to call them as support vectors. So support vectors are nothing but the samples which are closer to the boundary in the feature space, which will be influencing the decision making boundary, or which will be constructing the boundary basically. But the problem with SVM is it is not immune to noise. So whenever when a noise comes, it doesn't inherently have a filtering process. So it presumes that noise sample as one new support vector, and that can screw up your complete decision boundary. So that is the reason to handle that. Again, they had this slack factor into the SVM, and they had played around. But later on, they realized with in 1990s, as more and more data is flowing in, so why again discarding the complete information, or considering only few samples in the name of support vectors? Why don't we consider all the samples, and let's take the help of the information theory? So from information theory, information theory promotes the identity of impurity into the in the data sets. So to separate those data sets, and they're going to compute that impurity in each subspace or broken space, and so on and so forth. They are using something called the gene impurity index for identifying, okay, where should be the this complete feature space should be broken into or separated into. So this is again an iterative recursive process. This is actually a recursive process, not an iterative process like in neural networks. This is a recursive process. And the first node is termed as root node, or root node, or also decision nodes. People usually call it the decision nodes and leaf nodes. So the data will be fed, and at every decision node, a decision will be made in the name of thresholds based upon the gene impurity index, or information theory, or information gain. And the samples, as per the rules, will be placed into different category, or different small subspaces, and it will be recursively breaking the feature space into small subspaces until each subspace has all the samples from same class. Whenever you have all the samples from the same class, the impurity will be 0, right? So it will be complete pure subspace. So this is how they recursively break the subspaces, such that each subspace will be having only one class of samples. So then that final stage is termed as leaf node. So you have decision nodes, which will be trying to break your feature space into small subspaces recursively, and you will reach to a place where these each subspace is broken into small subspaces. Eventually, each subspace will be having only samples from one category or one class only. So this is a decision tree. And with that decision tree, people have been successfully done that, and they have achieved a lot of results also. And this is reiteration of the things which I said in the previous presentation, but it is more elaborative way. how we have done that, and we have taken the metrics like MSE and Pearson correlation, and the random forest is the best one. And this is the data set from which we have taken. So that is the data crawler code for sprintmotor.de. You can find it there. And the Python packages that were used are scikit-learn, Keras, and matplotlib. So scikit-learn inherently can do your SVM, random forest, Bayesian trees, and neural networks. But to involve deep learning, we have taken up the Keras. My personal suggestion would be go with PyTorch. But for abstract level of implementation of deep learning, more abstract level and more simpler level, people will go with Keras, which will be backed by TensorFlow. And for the battery life estimation also, we have taken the same approach. Like as we mentioned previously, we have taken the data set and we have uh, done it. Mm. And this is an cycle 1 for cycle 2, cycle 3. We have considered like how many less number of cycles we can take it and do the estimation is the thing what we have tried, and we are successful to some extent. But we should be always having a benchmark to deal with it. So what we have taken is we have taken as uh, one algorithm that is proposed by Stanford. So what they did is they didn't go with the learning approach. They have gone with an feature engineering approach based upon domain expertise. So what they identified is there is a relationship between the discharge rate and the voltages when you're considering this information and the number of cycles left. You can easily have an relationship, easy relationships. So based upon the change of charge with reference to voltage, uh, and if you take it on a log space and you have a linear relationship with the number of cycles related. So this is one thing they have taken, but they said that they are supposed to consider the first some more number of cycles, charge and discharge cycles. So then Hans Knollbloch has suggested, okay, let's not go with that approach. Let us take a CNN and an dense layer based approach so that we can have a better outcome. And they were successful on that. And they have done with using less number of cycles. And the beauty is there is chances like here they have taken some few tens of charge and discharge cycles to estimate what could be the final life left. But here they have taken few number of cycles in algorithm 2, but in algorithm 3 there is a new deep neural network based life estimation and voltage prediction using only one cycle. So based upon only one charge and discharge cycle, they are closely estimating the predicting the how much state of charge, state of health, or number of life cycles are left out. So they're able to predict that. So we are able to replicate the results, and we are successful in that aspect, like in replicating the results. And we have seen that yes, with one cycle of charge and discharge, we will be able to predict the things. And along with the remaining utility life in the name of charge and discharges, you can also have an battery state of charge estimation. So this is the algorithm that is proposed in the MDPA. So from this coming 5 to 6 slides, we'll be discussing about the papers that were that was mentioned in the MDPA, which is the latest release on deep learning for electric vehicles. So in this, they have introduced again deep neural networks, particularly LSTM units for state of charge estimation. So the unique, they have considered their data set to train the algorithms using specific profiles. Sorry. So state of charge, the data sets were mentioned in the paper, and the paper is given in the bottom part that is recited. And the challenges that they have addressed is they have this data set contribution is the thing what they're claiming. So they have obtained the voluminous of data set, which is supposed to be costly and requires a lot of laboratory restrictions. So contributions is like use of LSTM units makes the neural network behave suitable when using the time series. And they have LSTM based models, and the similar thing SOSH also can be done. Of course, they have basically said that how many types SOH can be broken into. That is an estimation methods basically broken into model-based, data-driven based, and hybrid methods. Here they have taken the data-driven based so that they can have a reliable prediction on battery SOH, even with that a thorough understanding of the battery internal structures. That is internal physics of a battery structure. Even the model is not predicted, is not provided, so they are able to have a state of health prediction properly. And again, the performance was verified, and they have said that okay, batteries require this special attention when used in EVs applications, and they have improper operations such as exceeding the suggested voltages, charge and discharges. So these are the challenges that they have addressed and mitigated while estimating the state of health. So again, the paper is cited in the name of state of health predictions. And there is another paper for the same SOH prediction, but instead of taking these neural network based approach, they have a fused approach, hybridization approach. So FCNNs and LSTMs. With that, they have achieved a better performance, is what they claim. But as they both are published in the same article time, so there is no comparison between the second method and the third method. And data-driven algorithm for the electric bus. So EV vehicles need not be restricted to four-wheeler retail vehicles. So they can go up to electric buses, to tractors, to varied applications. And they have seen that the algorithms that are being developed for these retail applications, cars, are also can be extended to larger systems like electric bus. And autonomous vehicles is one more prominent thing that they have taken. So there they want to do object detection for autonomous vehicles on EVs. So YOLO is you only look once, is one of the most prominent algorithm for autonomous vehicles or object detection using deep learning from images. So they have done a good job based upon the claims they make. But there are improvements on top of YOLOs because they have used some version 5 updations and they fused with their own custom model. But YOLO V10 also came up recently, which has very prominent performance. And there is something called as Vision Transformer. So if you recall in the first session, we were discussing about something called a transformer, like CNN LSTM transformer for prediction of solar energy. So that same transformer is extended to images from NLP to signals to images, and that is termed as vision transformer. So the vision transformer is employed for this image analytics, can also be used for image analytics, and there are more prominent purpose to this. And going beyond the conventional control, they are using deep reinforcement link based approaches also, because that is need of the hour, because you have very complex systems that are coming to play, and you want to have a DRL, but DRL doesn't take directly the data, but it is depend upon environment. So for that reason, there is one beautiful environment that is called as GEM. The citation is GOM, sorry, GEM. Oh no, it is should be a GEM only. But and you can keep on changing your converters, control signals, or controllers, and also motors, power converters, and all these things can be changed. And there are multiple reinforcement learning based algorithms that are already given as tutorials, and if you want to do anything on top of that also, that flexibility is there. So this is called as a GIM. So GIM is actually GYM is actually given by OpenAI, released by OpenAI. This can be done in Python, and you can develop the DRL algorithms also using Keras or PyTorch. And the pricing and scheduling also, where DRL is coming to play, and there were multiple stations, like charging stations environments that are available. Again, the GitHub link is given in the name of given in WSYCUHK. Okay. under reinforcement learning for real-time pricing and scheduling repository. Here also they have used reinforcement learning, and it is evident that you can schedule the inflow of cars and the pricing and the charging rates, so that a charging station, because charging station is not about taking the power and charging them, but they will be having some solar panels and also some energy that is being taken from the grid. So based upon the energy that is being taken from the grid and self-generated in the on the charging station, so what should be the amount that should be charged to the people so that uh, they can be profitable. So please keep in mind that these charging stations inherently also will be having some sort of a batteries. So those kind of things also need to be accounted into. And optimizing energy storage. When you have multiple sources, how this will be managed and stuff. So simulations, simulating EV activities, smooth control to avoid loss during the speed changes. So EV based data sets are readily available in name of the mm, sampled data, and also in name of your environments. So there is a lot of data sets that are available, which is very much the need for the deep learning. So you not to worry about a number of things, but you have to be worry about programming, because these will be coming from different sources and they will be using different libraries of different versions. So when that is the case, you might be having a conflict of libraries and versions, so you have to take care of that. Otherwise, majority of the information is available, and journals like IEEE and other publishers are also encouraging the researchers to upload their data sets. One example is for IEEE, you have a IEEE data port. So where the data that is used for individual papers, if there is a custom data, they are encouraged to upload it. So usually people are also uploading the data sets, because that will give the citations to their papers, and they have better visibility. Okay. For the whatever the task you take, outrightly you will be having certain data sets and environmental models, which you can take help of. And in this context, from a motor point of view, the same student who has done for grid integrations and stuff, he has also done for a DC motor, because that is where he started. He thought of going into PMSM, but later on he realized that maybe grid integration could give him a better potentiality, where he was true, because now he was taken up as a postdoc in China. Okay. And he's working on a professor who is having more than 1 lakh citations. So because he made an judicial call on switching from machine control, motor control to grid integration, and he was in good place now. So in motor control, it is like an speed regulations basically. So when a reference speed is being changed, the power converter has to generate the control signals, so that the converter, the final state of the motor, will be matching with the speed characteristics of your requirement. Speed characteristics will be with the requirement. So then he has compared with PI and the proposed model, and it was identified that the dynamic characteristics of the proposed model are better. And if you see, when the parameters of the existing model has been changed in the name of say L value or something like that, the PA has started to behave crazily. But again, the DRL has maintained its sanity and retain its performance. Okay. And that has been validated on multiple levels of L inductor values. But as keep on saying, the one of the drawbacks that we are still trying to mitigate is the steady state errors. But PA is having low steady state error, but more transient error. But to contrary, we have a better dynamic performance, but steady state error is something what we are fiddling around. Later on, it is identified that the quantization aspect is the play to blame, because the optimizer that we are using is the thing to blame. So again, that was being handled by different research scholars. And another research work is in the hybrid electric vehicles, where you have an IC engine and an uh, PMS motor or an electric vehicle, electric motor. So there should be an energy management between these two power sources. So that energy sources. So when to use IC engine, when to use electric vehicle, sorry, electric motor, so that the total fuel consumed and the total energy wasted for charging or discharging will be minimized. So that was also done, and that was published in one of the scientific journals by current PhD scholar, and he has been working rigorously on DRL methods, because one of the problem with DRL methods is sampling to modeling ratio, because you need more number of samples to model. So he is making a sample efficient models, so that with less number of samples you can have a better models that can be extracted. And this is a drive cycle. Usually a drive cycle we considered, so that what drive cycle, on which drive cycle we had achieved this performance. So maybe this makes sense people for the EV vehicle who are hardcore EV or mechanical. So basically, take home messages is like, uh, there are various problems that are being handled in electric vehicles from an AI expert perspective. But the first prominent thing is the battery management, what they're looking at. And next is the predictive maintenance. Next is the autonomous driving. Next, energy management and efficiency. And of course, smart charging and infrastructure doesn't directly go into EV vehicle, but from a charging station point of view, because that is closely related with electric vehicles. So charging stations, locations placement, how much it should be charged, at what rate it should be charged, and what should be the price placed, the dynamic price that is placed. So these need to be taken into account. So this is like materials discovery also it can be done, because in batteries you need new materials to handle different charging and discharging rates and the storage density or the packing density. So to all these things you should be having the material discovery also. And finally, improved models. Currently they are going with something called as physics informed neural networks. So it's not like, okay, neural networks can replace domain experts. It is like, okay, till this point of time domain experts has developed certain knowledge. So how can we infuse that knowledge into neural networks, or take the help of those knowledge into the neural networks, so we can perform better. So that is a synergetic approach that the people are doing now. So they are actually improving the existing domain expertise rather discarding them. So physics informed neural networks is something which is growing very rapidly, particularly in domains where they have very huge domain expertise knowledge available, and you want to upskill them, like not upskilling but improve performance to that. Because I have defined a model, now using this model, can ML make a better model? So this is the practice that is currently going on. So it is a synergistic approach, and this is working on very beautifully at this point of time. With this, I would like to emphasize that AI has its role to play in every aspect, and I have shown only the low-hanging fruits. There are various other ways also, other approaches also, or other tasks also that AI can handle beautifully and efficiently in electric vehicles. And I want to conclude with one statement, that AI will not replace humans or researchers. That's for sure, because that is too much claim to say. But one thing I can be assured, that people who are using AI can replace people who are not using AI. So AI gives an extra edge to the people, so that in the terms of research, or in terms of academics, or in terms of paper writing, or whatever. So when people are using AI tools for their research, or they're using AI for designing models, so those people will definitely replace people who are not going with taking the support of AI. Maybe in terms of research, maybe in the terms of paper writing, or maybe in terms of improving their model. So with this, I would like to conclude my session, and I'm open for questions.
Sir, I have a question.
Yeah.
Actually, you discussed about the reinforcement learning in some of the electrical engineering applications.
Mhm.
In one place, the controller has been replaced with reinforcement learning controller, RL. So, for example, if there is an existing controller like a PA controller, can we tune its parameters using reinforcement learning?
Yes, sir. That can also be done. Like tuning a PA, because the thing is you want to have say KPK values that are being given by your RL is what you're
Yes.
trying to do.
Yeah,
So
actually, the PA parameters usually will be fixed by some
yeah,
formulas, but we want to make it adaptive
ZS
using.
method or ZN method kind of a thing, Jen and
Yes,
Shannon method. So
yes,
okay,
yes.
Zen sir, I forgot, but I know it's short form. Okay, yeah, yeah, you can use it, sir. But the thing is, say end of the day, you are restricted by the mathematical expression of your PA controller.
Yes,
So which is a first order system, basically.
yes.
So, but your first order controller you're using to handle a non-linear higher order power electronic converter.
Okay.
Okay.
Yes.
So, is it feasible? Yes, it is feasible. Is it optimal? I cannot comment on that. But still, it will work. The reason is, majority of the power converters region of operation is so sleek that it will be having a linear characteristic in that region of operation.
Okay.
So that's why it will be working.
Okay.
Right. So when
Okay.
you are looking at a voltage that has to be generated, you're looking at only like 230 volts plus or minus 5% or plus or minus 1%.
Yes.
That in that region, it is expected to operate. That power converter topology is expected to. That is the information which I got from a professor. This is not validated by me. This is what I got from different expert from power electronics.
Oh, okay, sir. Okay, sir. So
Okay.
another question is, actually, we have a solar power plant in our institute,
Hmm.
and we have a data related to the energy generated
Hmm.
over a period of time. Let us say we have a data around 2 years data.
Okay.
So can we build a model which can predict the energy generated and
Yes, sir.
how much data is required? How to start with that? What are the features? How we can figure out these are the best features?
Okay. So that's where the deep learning will kick in. So deep learning is depend upon raw data only. You don't need to do any kind of feature extraction. So transformers is a good place to do. So recently there is multiple publications from our department, Sai Bob, I think. He's working with Dr. Kiran Tiparthi.
Oh,
So under his supervision, one person has published. He used transformers,
okay, sir.
and various kind of transformers. If you are going through his publications, maybe you will get a better insights into it. He used
Oh,
transformers.
okay, sir. Okay, sir. Okay, sir.
Okay,
Thank you, sir. Thank you, sir.
good.
Any other questions from the participants?
Hello, good evening, sir.
Good evening, sir. Tell me.
Sir, actually, I have one question regarding SVM.
Hmm.
Can it handle any missing data, sir?
Sir, missing data SVM cannot handle.
Hello?
Sir, SVM cannot handle missing data.
How can you explain me, sir?
Sir, missing data is like in a feature. When you have a feature for each example, say you will be having D dimensions, right? When you have D dimensions, you have to consider the vectors, the support vectors that has to be constructed. If there is a missing data, you don't know where to place that vector. For placing a vector, you need to have a complete data that is missing values. If it is there, how do you place the vector? Because those support vectors will be the governing aspects for your the decision boundary. Because if you look at the cost function of the SVM, it will be somewhere like alphas minus summation over alpha I, alpha j, yi, yj into xi into xj. So their xi and xj are the features, or the support. One will be the support vector, and their x should be complete. Decision trees can do that. What happens is, in decision trees can handle missing data, not because it inherently has a capability. Random forest and decision trees, you can separate the data, like you will remove the samples which are incomplete. With incomplete data, you keep them aside, and with the complete data you can train. And later on you can have another decision tree where you remove the features for which you are having missing data. When you have missing data, that means one feature out of d dimension features, maybe one feature or the two features are missing. What you will do is, you will remove those features, and rest of the d-3 features or d-4 features you will consider decision tree. So this is how random forest will play a look around trick for using it. But SVM can't do, sir. Even neural networks can't do.
Okay, sir. And one more question, sir. Actually, as we know that there are 3 or 4 types of kernel. So how we are selecting that particular kernel?
In SVM.
Yes, sir, in SVM.
Sir, in SVM, the majorly used kernel is an RBF kernel,
Yes, sir.
radial basis function.
Yes,
So
sir.
radial basis function kernel is used over the polynomial kernel or anything, because when you look at kernel trick, if you go through the kernel trick, the whole idea is, rather computing those values in higher dimensions, we want to use a kernel to compute it. So there is the whole idea of kernels. You want to project it. Now, but when you look at RBF kernel is one of the most commonly sought out kernel in
Yes, sir.
respect to other kernel. The reason is, RBF kernel, if you look at it, RBF kernel is 1 by root 2 by sigma e power minus half of x minus mu by sigma whole square, something like that, right? Where x and mu will be one support vector and data. Okay. So when you have something like e power minus half into something, that boils down to actually e power xi into xj. 1 plus xi into xj, you can make it. So that becomes an infinite series basically. So when you have infinite series, you are bringing the data set from, or data representations from infinite length or infinite dimensions. So that's why RBF theoretically is preferred over other things. You will not be worrying about the blowing of the information, blowing of the values, because when you have an e power x expansion, you will be having an polynomial denominator also. So you not to worry if it is going like x cube, x power 5, x power 10, it will be divided with an n polynomial, sorry, n factorial. So you not to worry. So RBF is the most preferred, sir.
Okay, sir. Thank you, sir. Thank you so
Good
much.
day.
Any other questions from the participants? Welcome. Any other questions? You can feel free to ask. Okay, no questions. We would conclude these sessions. Sir, Fani Krishna sir, once again on behalf of organizing committee and Department of Electrical Electronics Engineering, I wholeheartedly thank you, sir, for accepting our invitation and being a part of our FDP. And very nice, informative, and insightful sessions. It was because these sessions were exactly in line with our theme of our FDP, and we are very grateful to you, sir. And we are looking forward to collaborate in future also. Thank you so much, Fani sir. Thank you.
Thank you very much, sir, Dilip sir and Srikanth sir, for inviting me and giving the opportunity. And also I thank the Vishnu management for organizing such sessions and encouraging faculty like you. Good day, sir.
Thank you, sir. Thank you very much. Dear participants, we will have feedback session from the participants, and then vote of thanks, followed by test sharply at 7 p.m. So So I request we'll take 1 or 2 minutes break, 1 minute. And then we'll start.